Hi, I'm Alexis, I'm CTO of Numberly. I will be talking about our experience in replacing MongoDB and Hive for a process-intensive workload using Scylla and what we learned in doing this and how we are now running this in production.
So I'm Alexis, you can find me around as Ultrabug. I'm a CTO at Numberly, and I'll get down to what is Numberly and what we do, and why then we are using ScyllaDB. I'm living in Paris, France, which I guess you already can tell by my accent, so I'll do my best not so much to show it. Since there is number in our company name, we like numbers, right? So in Paris, in case you didn't know, there is one Eiffel Tower, for example. In France, there are 2 soccer World Cups that we brought home, and we are apparently very proud of it. I don't know, I'm not into soccer anyway. And as for myself, I've been working 15 years in the data industry, which I feel old to say, but I have to disclose it at some point. Apart from this, I'm a Pythonista. That means that my main language when I develop things is Python. I'm an open source software, and it shows as well enthusiast and contributor, and a proud contributor as well of ScyllaDB open source. And when I'm not wondering about projects and open source projects, I'm also a Gentoo Linux developer. So this is it. Numberly, what we do, I will give you a bit of a business context so we can get into why and how we're using ScyllaDB over here in production. So we are a digital marketing technologies. It's called MarTech, and that's how it's called. Doesn't sound very nice, but that's how it is. We are an agency. We handle relationship between brands and companies and people, like you and me. So we do people-based marketing. That means that to achieve this, we leverage the value of the data that we can get and that we collect and help our customers do something out of it and do something out of it. So we are using a lot of different data sources and a wide range of data types. We see data as events in our company, so this has a lot of implications in how speedy we have to be, because the value of data is higher when it's hot and when it's brand new. So that means that in our line of business, we are putting a lot of efforts and in mixing and correlating this massive amount of data and different types of events. And you can see those data and events because they are coming from different sources. They all have their own identifier, right? So a user can be something on one data source and something else on another. And we'll get into some examples now. But you can think of those identifiers as primary keys. Okay. Few examples of what the data sources can be. When you talk about web navigation tracking, it's done through the browser, so usually the identifier here is a cookie ID. You have CRM databases. CRM stands for Customer Relationship Management databases. That's basically what a company or a brand knows about you as a customer. Those ones are usually prepared, and the main identifier is the email address, usually, or some customer ID that they can have. Then we operate this data, so we are connecting with a wide range of digital platforms, which all have their own ID as well. So it can be web-based platforms such as, I don't know, Google Ads, which will see you as a cookie ID or some kind of hash of email address or any kind of other identifier. Then you have also all the mobile landscape. So it's a device ID, IDFA, JID, etc. I guess you get it. The key aspect then in our business, what's really important is to be able to, for this, we really need to be able to synchronize and translate all those identifiers between all the sources that we handle and all the destinations that we use. For this, we use what we call ID matching tables. So the principle is pretty simple. You have a reference population that you will, let's say, select. And then you have this ID matching table that when you will join, and join is a pretty expensive operation in the database world. And I won't explain you how power hungry it can be. And then you get a matched population that is usable by the partner. This is how they see you, us, or the people that we're talking to and establishing a relationship with on their own network. What it means is that those ID matching tables, they are queried and updated all the time. Every time we know a new ID matching, we will update it, and then we will be using it all the time. This is a very high read and write workload. So this is very power hungry. Let's take a real-life example so we are all on the same page. Let's say recently Wikimedia has been doing its fundraising. So let's say that they are contacting us and they say, okay, we want to display a banner ad to ask for the previous donors of the previous fundraising that we know by their email address, and we want you to display an ad to them because they are more likely to donate again. And for this, we will use what a third-party partner like AppNexus or Google Ad Exchange to buy those spaces. But the first thing that we have to do is actually to translate an email address to a cookie ID that is recognizable by those partners, right? So let's say on the first one, we have to be able to translate the generous@coconut.fr to cookie ID 123, that is the cookie ID that Google knows about, so that when the user with ID 123 will be browsing the web, we can buy and display the ad for the Wikimedia Foundation. So it's selection, activate, and matching. There's a little glitch in the presentation, and then we activate. This is how we use the data, basically. Fair enough? All right. So how we do it, how we did it yesterday, some months ago now. So we have events coming in. It's a typical Lambda architecture, right? So we have a real-time pipeline, a batch pipeline. We use message queuing. Then all those events and all these and the ID matching tables, they reside in the MongoDB. Then we have real-time programs querying it one event at a time to make sense out of it and use it somehow. We have the same one for the batch calculation pipeline. So we use HDFS. All of this ecosystem on the batch pipeline uses Hadoop. And we use Hive as the database engine there. And then we can run a batch operation in this. What you can already see is that for a single input source events, we are using two databases. Why is that? Is that it's simple. When you want to query or do a simple select in Hive, it takes minimum 20 seconds. It's just the time that it needs to fire something. So it's good, and it's meant for batch calculations. MongoDB, on the other hand, you can get milliseconds queries, so it fits well the real-time programs. But there is no way that one or the other could match both workloads at the same time. MongoDB couldn't sustain all the read throughput that the batch calculation workload would put in it, and Hive just can't do millisecond or sub-millisecond queries. So we end up having a lot of code base that is related to making sure that the data is consistent between some real-time NoSQL database and some not real-time at all Hive database. So there's a lot of engineering. It's really a burden to maintain and to operate over time. Even more when you care about data consistency like we do. That's when I came across Scylla. Those guys, they were advertising, okay, we can do a lot of writes, we can do some really heavy reads, and we can do it with some kind of linear or very, very low latency. I said, well, okay, so that means that I could be doing this. I could be replacing MongoDB and Hive with just a single instance database and remove all the code associated to it. When we did this, because now it's in production, we removed 1/3 our code base, actually, when doing this. It was pretty awesome. So the bet is Scylla can do both and sustain both the workloads. It relates well to what Glober was saying this morning. And I went for the POC. For this, we run a lot we run on bare metal on our own data center. So I had some crappy machines lying around in our basement, and I decided, okay, let's try this new technology in the best omens possible, and let's try to get some shitty machines to bring up this POC. They are not even consistent between them. It's SAS spinning disks that have been reused for a long time. My goal was here to say, okay, if those 3 crappy machines can compete somehow, and I wasn't expecting much at first, with our production, Scylla has a good chance to get in. So the first thing was find the right schema model. Obviously, I'm not coming from the Cassandra world, so I had no background experience in this. So you apply query-based modeling. This I had experience in because we are using MongoDB. And then I apply as well test-driven data modeling. So test-driven is you write some tests to actually validate that given the input, your schema model will always give you the right output, right? So it allows you to iterate on the schema model and don't and avoid trying over and over again or some variations of the code. So it helps getting better. The keyword here is usually denormalization. In our case, we denormalize 3 times, so we have 3 different copies of the same data, but now inside one single database. So I prototype using Python. One thing interesting I learned in this, and I wanted to share it, was about the clustering order effects. It's for reference. The data model here is what we have. It's just sort of a log. Okay, so you can see, we don't overwrite any row. We just append them one at a time, over and over. And the key clustering column to look at is the date. One of our questions was, we are in our workload mostly, not only, but mostly, we are interested in the freshest data, the latest data that we have, right? And a key thing that the clustering order, it defaults to ascending order. That means that when Scylla writes the data on disk on the SS tables, the latest value are at the end of the SS table. Meaning that when you look up for something and you want the freshest data, it has to go down all the SS table to get it. So the trick was to just reverse the ordering order on the clustering order to descending, and then the latest value are now at the top, and it reduced read latency. It's the kind of trick that you can, in my opinion, only get by interacting with the ScyllaDB guys. So thanks again for this magical trick. Then I set up, of course, scylla-grafana-monitoring. It's really easy to set up, Docker-based. I use Cassandra test to get acquainted with it. There are some key graphs. I put them here for reference. One nice tip I had as well was to reduce the scrape interval. When you do this and you want to iterate over your tests over and over, so reducing the scrape interval will just allow you to have more data points in a smaller period of time. So you will see the results of your test faster. Then I prepared some reference data and to get some reference metrics. In our case, I took 10 million population, 400 million ID matching table. What is interesting here is you have to find a ratio that represents your data cardinality and the typical volumes that you have. I was not interested in putting everything in Scylla. I just wanted something that I could relate with in the real world. So, and we also decided to test this on our production stack. So you may have your opinion, but I thought it was very informative to just try and run and take this population and just do like we do usually on our production stack. So we have not been driven in our conclusion to using Scylla in production by benchmarks. It was not only about benchmarking. It's not a benchmark. I will give you times, but they are not meant for benchmarking. It's the whole thing that is important. So it runs basically like this. So this is was the current state, right? So you have your population on Hive. We were using Spark, and since we are in Hadoop cluster, all the Spark workers are spawned and scheduled by Hadoop yarn. So it's Spark 2 plus yarn, and then it splits this population, do the ID matching table, and then we do a count. When the Hadoop cluster is idle, it took us like 2 minutes. When the cluster is under normal load, it takes 4 minutes, and then when the cluster is overloaded, meaning that yarn has trouble finding some empty slots or empty containers, it's called, it could take up to 15 minutes to do this join between 10 million and 400 million. Okay, now the fun part begins. Let's try using Scylla. Before you go, remember, there is 2 scenarios that we have to consider here. The hot cache and the cold cache scenario. When you are in cold cache, no, it's like as if you just started your cluster, so all your reads, all your lookups, they will be disk I/O bound. What you're trying to do here, and what we were trying to do is, I want to break Scylla. So my goal was to break it, push it to its limits. I was reaching, and you were reaching for 80 to 90% usage, load usage on the Scylla cluster. If you don't reach it, it means that Scylla is not the bottleneck. Your code or the pressure that you put on your test is just not enough. So to evaluate the actual load it can take on those 3 crappy machines, I had to push it to its limits. So it looks like this. I just replaced the ID matching table that were lying on Hive on the bottom part in Scylla. And I just ran it again using the Scylla, the Spark Cassandra connector from DataStax, which comes with the nice and handy join with Cassandra table. So, okay, I'm a Python developer, but I could manage to code some Scala. I put it here for reference. And I put also the versions that I use on this because they have some different behavior. So this is how it works. I learned some things doing this. At the time, the ScyllaDB guys didn't write some posts about how to tune Spark, so we went through debugging this extensively. I almost removed all my hair while doing this, but anyway. I finally found something, and this is basically some key things. So I put even the options that we use for reference, but using a fixed number of executors, it was interesting and important because you are iterating. So by default, it's dynamic, so it's based on what's available. So if you want to have a consistent measurement, you have to fix it. Then the split size for read performance really helps. The adjusting reads per second helped you get from 80% usage to 90, 85, so it's fine-tuning this one. The number of connections, you will hear about it a lot, I guess, through the conference. It's a main driver of the performance. And since then, I put them as well here for reference. The Scylla guys have been working on a series of posts which are very, very good. So I encourage you to read this, and you will get what you need. OK, the results. Cold cache scenario was 12 minutes. Hot cache scenario, 2 minutes. So when I saw this, I went like, wow. Guys, these 3 machines, they can already compete with an idle cluster of more than, at the time, 70 machines. Hadoop cluster, it is. So, OK, there is always the yarn scheduling that comes into play, right? So it's Spark plus yarn every time. But I was pretty impressed. But still, it was Scala, so it was good, and it was representative for one part of our workload. But the data science and a lot of our algorithms or or real-time systems use Python. So I couldn't satisfy myself with the Scala results, right? The problem is, okay for Scala, but in Python and PySpark, for example, there is no join with Cassandra table available. So all this token-aware and clever thing doing the join, I can't use it. So I thought about it for a lot. It stressed me quite heavily. I was pretty upset, and at some point I got mad and I said, maybe I don't need Spark 2 at all. Basically, what I need is to load 10 million rows, right? And for every row, maybe I can just fire as much lookups in parallel as possible and match them from Scylla and then just do a count. So I went into this crazy idea and I accepted my own challenge. For this, I just needed the equivalent of Spark, so a distributed computation framework in Python. And luckily for me, there's more than one, but the one I picked was Dask. So it looks like this. Basically, you can replace what you saw with Spark 2 with Dask, and then I just ran this with the same number of workers that I had from executors for Spark 2. And the results were pretty convincing. I was already doing the same without all the days and I can say weeks of tuning Spark 2, right? So cold cache went down to 6 minutes and hot cache 2 minutes. Great, it's looking pretty fine, but I couldn't satisfy even with this. I had to understand what's lying behind this. So I found that the Hive, loading from Hive to 50 seconds, if I can get and load this data faster than 50 seconds, I could even beat Spark 2 and on Yarn performance using Dask. So I switched from Hive, those 10 millions from Hive, I switched to Parquet files, which is a columnar data format to store files, and I put them on HDFS, and I used Dask to load it, and boom, I won 40 seconds. And now I was faster than Spark 2 on Yarn. And I got almost to 1 minute to do this join, whereas in Spark I was doing 2 minutes. Great. I learned something out of it. So these are some tips. Execute concurrent is really important when you want to fire up a lot of queries at the same time. Of course, prepare statement. This is a no-brainer. Increasing the concurrency that defaults to 100. Using asynchronous connection class is really important as well. It has a huge effect. But most importantly, the two things that allowed me to load these Parquet files as fast as 10 seconds was the usage of HDFS3 plus PyArrow. I don't know if you know the Apache Arrow project, but if not, check it out. It's magical. I put the code sample in here because it took me a little while to find out how to do it properly and load it that fast. So this is how I did it. You have it for reference. So yeah, I guess I fell in love with Scylla at this point. I was like, okay, man. Operational burden out, every consistency problem out, all this complicated code base and stack to keep everything consistent out, and dramatic performances. So we went into production. Today, we started with 3 on 1 data center. Now it's 6 on 2. We discussed, obviously, a lot with the ScyllaDB guys to get the right hardware, etc. So we chose the specific series of Samsung NVMe that they had benchmarked. So it's some pretty serious machines. They run on Gen 2 Linux. Yeah, couldn't help it. It's now a multi-DC setup. We use Ansible to provision and do all the backups for everything. It's monitored by the scylla-grafana-monitoring, even though we have our own monitoring and our own Grafana as well. We prefer to stick with theirs because it's well done and they update it, so it's pretty cool. And all the housekeeping of repairs, they are handled by Scylla Manager. Thank you very much. And I guess we have some time for questions if you have.